So now let's come and see how cloud computing fits in here. And clouds are actually, technically, what they are is clear. They're a bunch of computers in an incredibly efficient large data center, which uses economies of scale and optimal design to be very efficient and very cost effective. They were originally designed to meet the needs of public-facing Web 2.0 e-commerce or social networking or search sites. But now perhaps it's better to consider clouds as the optimal giant data center. And the clouds we happen to be studying, which are the ones typically used in public activities, they have to have a good internet connection, or else you wouldn't be able to access them. And there are also clouds which are private clouds, which are giant data centers, but they're not necessarily optimized so significantly for internet access because they're running the internals of a corporation. So virtualization is very important in clouds, and that's the most abstract virtualization is just an abstraction. It says, you have a job, we have thrown the job at the cloud, we have no idea where it runs, whether it be in which side, which part of the globe it runs, and how many other jobs are running at the same time. And that allows this highly efficient, cost-effective model. We support that abstraction with a so-called hypervisor, which allows us to support images, because that image allows you to package the complete job as the operating system plus the application. And that's pretty important because if you take any bunch of software, it tends to be highly sensitive to the operating system, and it is very difficult to get that application to run on a general platform. Grid computing had lots of trouble in this regard, because grid computing tended, at least at the beginning, to be looking at distributing jobs, not distributing images, and the jobs were just the application without the operating system. So the use of images is technically very important because essentially any image, each cloud tends to have its own exact image format, but once you produce an Amazon image, it will run on any Amazon machine, and there's no problem. Whereas if I take any job, the chance of it running on any given operating system is essentially zero. Unfortunate, but true. And this allows us actually to pack these, because a given machine can have support many images and many virtual machines, essentially. We can pack many applications onto a single server. They don't interfere very much with each other. That's not totally true, because if one uses a lot of memory bandwidth or a lot of network bandwidth, that impacts the others. But there's some performance issues, but not dramatic, as long as we run the machine reasonably sensibly. And so we can pack applications into a single server, something which would be impossible if those applications were running as application software and all sharing the same operating system, because, as I said, we would need a different operating system optimization for each application, and the operating system would mix up the applications and produce various undesirable features. I'm sure you've used your PC and had it crash in one application, destroying all the beautiful word processing you were doing in a different application. That's happened to all of us, I'm sure, many times. So not only is the interference affect performance and robustness, it also affects security. The security model between virtual machines is much more robust than that between processing, the component which runs on a single OS. So then Amazon noted it can actually had idle machines, and it could rent those idle machines out, and it used virtualization for the maximum efficiency and security of this renting model. Then if they have enough machines, you get elasticity, namely they have enough spare machines which may be actually switched off when they're not being used. And you can rent as much as you want, except at peak times. And this partly bears in mind that actually the cost, when you run a computer center, the cost of the machine is not probably not a dominant part of your costs. The actual running of the machines and supporting of them is expensive. And so you can have a lot of switched off machines which you switch on when somebody wants. And if you have 100,000 or a million servers in a single cloud and you kept a few percent idle, that's a lot of servers waiting for people to come along and demand them in an elastic fashion. That's a weakness of the days. Some of the days are sort of private clouds or science clouds. They're not big enough maybe to actually have a significant reserve capacity. And whether you switch them off or keep them switched on and just bring them to bear is a technical issue, which there are lots of papers that tell you what the trade-offs there are. And Amazon, I'm sure, will never tell you some of the details here because it's proprietary. And one of the features of this field, which we've discussed more than once, is a lot of the innovation is happening in companies, and those companies do not always tell you what they're doing. In fact, I would say they typically don't tell you what they're doing in detail. So we're going to use a service model for our clouds. And the service model generalized what's familiar from the web, and it's actually what's familiar from this pipeline: data, information, knowledge, wisdom. Namely, the world consists of entities called services which gobble up data and produce data. Well, actually, as I have stressed before, then actually, if you start with data, maybe they produce information. And if they start with information, maybe they produce knowledge. And if they start with knowledge, maybe they produce new knowledge or wisdom or decisions or policies or what have you. Anyway, we have a world where we build things from these services, which on a while ago there was a slide which said we called those filters, because a filter is something that changes something. Or there could be maps in the MapReduce framework. These are just entities that get in something and put something else out. And that's a service, so services are very important. And this is a different way of building software. Previously, when you wanted to do two things, you tightly coupled them by making them as methods. So you have a method number A and a method number B, and you would call A and then you would call B. But the difference model is to put A in a service and B in a service. A spits out data, B receives that data, and then B spits out data, which maybe goes back to A, or more likely goes on to another service C, which service C may actually store the data on some place. Well, maybe again, this data is information. So this is just loosely coupled, the coarse-grained service model, and today's compute architecture strongly favored coarse-grained loose coupling because that's more flexible and easier to evolve. Namely, if service A needs to be improved, you don't have to touch service B. Whereas in this model here, when I take a package and tweak up one part of it, I actually effectively tweak up the whole thing. So there's dependencies between the different services, which are not present here except on the dependencies from the message format. So you have to have message standards, and there's a lot of work on message standards. Then if we come to clouds, we have these various different service levels. We have infrastructure as a service, which is renting out the hardware. Platform as a service, which is the capabilities, features, such as database, MapReduce. Those are middle system level capabilities. That's platform as a service. We use those to build the types of things we discussed on the previous slide, which are application services, the filters that transform data into information. And all of this is built on network as a service, which is networking, and that's also becoming software defined using technologies like OpenFlow and software defined networks. That's captured in this slide here, which tells you there's a stack. We have here we have network as a service at the bottom, OpenFlow. There's a US project called Genie investigating this. And this allows you to find the general network between the computers you care about using software. Then we have software where we have software-defined computing. Those can be virtual clusters. They have hypervisors, or they could run directly on the computer. And we, of course, have the operating system at this level. Then we have platform as a service, where I pointed out things like MapReduce. If we were doing parallel computing or high performance computing, we would have libraries like Petsy or grid technologies like Saga at this level. We could have computer science, say compiler tools or sensor tools, or maybe even data algorithms would be placed at this level. Then we have the software as a service. Maybe the software used in this class will be placed at that level. The computer science researchers will produce software at this level. Chemistry simulator will be at this level. Our astrophysics simulator at this level. Our recommender system will be here as a service. And then finally, on the top, we actually have the support of the computing as a service, which allows you to tells you how to use custom images, prepare a course. They will consult when you screw something up. They would help you to build portals and provide archival storage. So this is a stack of modern computing, and we're effectively used to be that a single organization provided all of these. Now the infrastructure as a service may be solely provided by public sources like Azure and Amazon and Google, and you only do the support. You need to use platforms produced by other people, and you build software, and you use, say, your local university might support your use of this modern environment. So here is this thing put together again for research as a service. To do research as a service, we build software as a service. We put it on infrastructure as a service, or you could say it's hardware as a service. We use particular middleware or system services as platform as a service. And that gives us what another way of thinking about cyber infrastructure is research as a service.